This is a problem that we analyzed in example 9.9, but now we're going to find the acceleration of the JoJo and the tension in the string. Now just to recap, this is going to be a JoJo consisting of a solid disc with the radius r and the mass m. So we got the JoJo, we got the hand, and we have a picture when it drops down. We have the velocity of the center mass being equal to 0, and omega being equal to 0 as well. Now to make a better picture, we just drew a x-axis, a y-axis, and we have the circle representing the JoJo. So we have the central point right here, the radius is this line. On the y-axis we have the weight dropping down, and the only force that we have besides the weight is the tension representing the string up here. So a couple things to know before solving the problem is that in one revolution there's 2 pi, the angular displacement, but also in one revolution the velocity of the center mass is being equal to the angular displacement times the radius divided by the change in time. But we can rewrite the 2 pi being equal to delta theta. So delta theta divided by the change in time is the same thing as omega. So for the velocity of the center mass in one revolution, we have omega times r. In addition, we also know that the acceleration of the center mass is being equal to the radius times the angular acceleration. So in this case, the sum of all the forces in the y direction is going to be equal to mg minus the tension, but the tension is the unknown. So we need to find the sum of the forces of the torque is going to be equal to the tension times the radius, and that's going to be equal to the moment of inertia of the center mass times the angular acceleration. So for a solid cylinder, the moment of inertia is going to be equal to 1/2 the mass times its radius squared times the angular acceleration. But we found one thing at first. Right here up on top, we found that the angular acceleration, the acceleration of the center mass is going to be equal to the radius times the angular acceleration. So the angular acceleration could be rewritten as the acceleration of center mass divided by r. That's what we put right here. So as we continue solving for the tension, which is the unknown in this case, is going to be 1/2 times the mass times the radius times the acceleration of the center mass in the y direction. And that should give us we got that t is going to be equal 1/2 the mass times the acceleration of the center mass. So as we said before, the sum of the forces in the y direction is going to be equal to mg minus t being equal to m times the acceleration of the center mass. So we continue solving for that, and we say mg minus 1/2 ma of the center mass in the y direction, the value we just found being equal to the ma of the center of mass in the y direction. So we cancel out the m's and we get the value of g being equal to 3/2 times the acceleration of the center mass. So the acceleration of the center mass in the y direction should be 2/3 times g. Now that we have the acceleration, we can now find the tension. We said that the tension was 1/2 the mass times the acceleration. So we have 1/2 times the mass times 2/3 of g. We cancel out the 2, and we end up with the answer being tension equals 1/3 mg.